The elevator problem is a classic problem in physics. It serves a few purposes. It's a reminder that weight is a force. Okay, so we calculate force of gravity by multiplying mass times acceleration due to gravity. It's also another problem in which we can practice making free body diagrams. And lastly, it reveals the difference between internal versus external forces. I don't think it's been stated yet that Newton's second law should be written as a vector equation that says acceleration as a vector is the sum of all forces as a vector divided by mass. Well, actually, we've said that. Here's what we haven't said yet. It's only the vector sum of all of the external forces that act on an object. So that begs the question, how do you identify the difference between external forces and other internal forces? So hopefully this problem illustrates that. But let's just jump into it and see if we can reveal the difference between internal and external forces along the way. So we're told there's a 75 kilogram person standing on a bathroom scale inside of an elevator. There's our bathroom scale. The elevator by itself, if the person weren't inside of it, has a mass of 425 kilograms. So there's a few questions asked along the way. What's the tension in the cable when the elevator is at rest? So let's practice making free body diagrams. What's the tension in the cable when the elevator is at rest? So I've got a few choices. First of all, when we make a free body diagram, we just draw a dot. So what does that dot represent? Does it represent the person? Does it represent the elevator? Or does it represent the combination of the person and the elevator together? Well, I'm free to make a free body diagram for any one of those choices. And in this case, I want the force between the passenger's feet and the ground to be internal. I want it to be a force that doesn't matter. So if I were making a free body diagram just for the person by themselves, I couldn't ignore that force. The bathroom scale pushes up on the passenger's feet. If I made a free body diagram just for the elevator by itself, then that very same force that's pushing up on his feet is represented on the elevator as his feet push down into the elevator. That's just a statement of Newton's third law. If the elevator pushes up on his feet, then his feet push down on the elevator. But I don't want to have to show that force. So if I make a free body diagram for the combined system made up of the passenger and the elevator, then that force of interaction between his feet and the floor becomes internal. So that's what we have here. The mass is the mass of the whole system, which you can easily convince yourself is 500 kilograms if you add their individual masses together. So what forces are external to that compound system of the person in the elevator? Well, there's the cable that pulls up. And then, of course, there's gravity pulling down on the whole system. So here we go. There's an upward force in my free body diagram. We'll label it as T for tension. And because we're told that it's at rest, that means not only is the velocity zero, we have a case where acceleration is zero. That can only be true if the net force is zero. We know this is an example of the state of equilibrium. So for the net force to be zero, the upward force and the downward force should be drawn of equal length to show that they cancel one another out. So the only way the net force is zero is if the upward tension is just as great in magnitude as the downward pull of gravity. So there it is. That's how we can solve for the tension. Just find the combined weight of the passenger and the elevator. And so we get tension is equal to 500 kilograms multiplied by, let's make life easy. And instead of calling G 9.8, let's just round up and call it 10 meters per second squared. Okay, so we get a tension of 5,000 newtons. What would the scale read if the elevator is at rest? So still talking about elevator at rest, but now we're being asked what does the scale read? We're not asked what is the tension. And so now I have to consider a case where I change that scale reading from an internal force to an external force. Well, that would be the case if I made a free body diagram just for the person exclusively. Now that scale reading is no longer internal, it's external to the object in question. So we make a dot in every free body diagram. This no longer represents the entire system. This dot now just represents the person by themselves. So it's a mass of 75 kilograms. And again, there's an upward force. This time, the upward force is equivalent to the reading in the bathroom scale. And the downward force, again, is gravity. Hopefully, it looks like I've drawn those two of the same length. That's the intention anyway, because again, we're told it's at rest. Acceleration is 0, so the net force has to be equal to 0. I actually want to give a different name to this. I don't want to call it the scale reading. So whether the person is standing on a bathroom scale or not, it doesn't change the force of contact between their feet and the ground. I suppose by putting a bathroom scale in between the feet and the ground is just a way to register how strong that force is. So if you were standing on level ground, what would be the direction of that the ground pushes up on your feet? Does it push up and to the left, or does the ground push against your feet up and to the right? Well, of course, I think we'd argue that the ground just pushes straight up against your feet. But notice that that direction of push is perpendicular. It's 90 degrees to the ground itself. Okay, well, what if you were standing on an incline? Then does the ground push straight up? I think in this case, the ground pushes up and to the left. And notice that that's 90 degrees to the surface. Now, mathematicians have a lot of different names for 90 degrees. Sometimes they'll say that's perpendicular, or they'll say that's orthogonal. We can say it points at a right angle. And we can use the word normal as well. All of those mean the same thing, right? And so the ground pushes perpendicular. The force from the ground pushes perpendicular to the ground itself. The force from the ground is orthogonal to the ground itself. It's at 90 degrees. It's at a right angle. I'm going to use the language normal. I'm going to say the force from the ground is normal to the surface. And so in that regard, the scale reading in the case of this person in the elevator is a force that's normal to the floor of the elevator. So I'm just going to use this symbol N as a reminder. So contact force and normal force moving forward are interchangeable terms for us. Okay, so for the net force to be 0, the normal force has to be just as large in magnitude as this downward force of gravity. So 75 kilograms multiplied by 10 meters per second squared gives us a normal force of 750 newtons. What would the scale read if the elevator accelerated upward at 3 meters per second squared? Well, that changes things. So I'm still going to make a free body diagram for the person, and I still have this downward force, mg, but the only way that there can be an upward acceleration is if the upward force is greater in magnitude than the downward force. Now that upward force is still the force that's being measured by this scale. It's still this thing that we would call normal force, but we just note that that normal force has to be greater in magnitude than the force of gravity, otherwise it would not be accelerating upward. So let's just start by stating Newton's second law. Net force equals ma. But what is the net force? Well, it's the difference between the upward normal force and the downward pull of gravity. So N minus mg equals ma. We're being asked to solve for the scale reading. In other words, we're just asked what is the value of that normal force. So we just need to add an mg to both sides of the equation, and we have n equals ma plus mg. If you want, you can factor out the m. So normal force is mass times a plus g. So we just need to plug in the numerical values. 75 kilograms multiplied by 3 meters per second squared plus 10 meters per second squared. In other words, 75 times 13. And we get a scale reading of 975 newtons. What's the acceleration of the system if the tension in the cable is 3,650 newtons? So because the question references the system, and we have to figure out something about the tension, we need to make a free body diagram for which tension shows up. And by the way, why didn't tension show up in this free body diagram when we are considering the person? After all, the person stands in this elevator, and that tension pulls upward on the whole system, so why isn't that tension pulling up on him? Because free body diagrams only show the direct external forces. So this tension is the only reason why the floor pushes up the way in which it does. So it's as if that tension is transmitted in a way, but not directly to this person. So the only forces that are directly acting on him where the ground pushes up and gravity pulls down. We would only show tension as a force in our free body diagram if we were making a free body diagram for the elevator or for the system that includes the person and the elevator together. So that's what we're going to do once again. This free body diagram no longer represents a mass of just 75 kilograms. This is the mass of the whole system, which is 500 kilograms, and the forces that are applied to the system is the upward pull from the tension and the downward pull of gravity. Now wait a minute, we're told the tension is 3,650 newtons. And let's see, I know I'm going to put in this other force, mg, for the weight of the whole system. That's 500 kilograms times 10 meters per second squared. That's 5,000 newtons. So this is definitely less in magnitude than the weight vector. So when I draw in the weight vector, I want to keep everything to the correct scale. So if this represents 3,650, this needs to represent 5,000, so I draw it longer, right? So mg is 5,000 newtons, tension is 3,650 newtons. What's the acceleration of the system? Okay, well, start by just writing a statement of Newton's second law, net force equals ma, and then based on our free body diagram, what does the net force appear to be? So in this case, the net force appears to be, well, let's do it this way. Let's just always choose a frame of reference such that the positive direction is the direction of the larger amount of force. So since mg is greater in magnitude than the tension, let's think of down as positive. In that case, the net force would be mg minus t. So mg minus t is equivalent to ma. We're trying to solve for the acceleration. So it looks like a is equal to mg minus t divided by m. So we have acceleration is equal to 5,000 newtons minus 3,650 newtons, all divided by 500 kilograms. And this gives us an acceleration of 2.7 meters per second squared. Now, notice our answer comes out to be positive, and positive means down, so it means he's accelerating downward. Now let's look at, there was an additional question. Is the elevator moving up or moving down? So you might think that, oh, the answer came out positive, down is positive, so it's moving downward. That's not necessarily the case. It's accelerating downward, but that doesn't mean it's moving downward. It could very well be moving upward, yet accelerating downward. If that were the case, it would be slowing down. The fact that gravity is stronger than the tension would just mean that it slows down as it rises. Of course, another possibility number 2, is that it's moving down. Well, in that case, that would mean that it's speeding up. So that's something interesting to note about free body diagrams. They'll never tell you necessarily what the direction of motion is. They'll only tell you the direction of the acceleration. And it's possible to move up, yet accelerate down. Okay. Watch out for that pitfall as you solve problems involving Newton's laws of motion. What's the reading in the bathroom scale when the elevator ascends at a constant 5 meters per second? So again, since we're asked about the bathroom scale, let's make our free body diagram represent just the person, so that scale reading is no longer internal and becomes external. Now wait a minute. Constant speed implies an acceleration of 0, which implies a net force of 0, which is a description of equilibrium, which means it really doesn't feel any different at all to stand in an elevator that's at rest versus standing in an elevator that's in motion at a constant speed. Now maybe it sort of rattles around and you can feel some bumps if it's not a really smooth ride, but if you can construct a really smooth riding elevator, you wouldn't know whether you were at rest or in motion. The feeling would be exactly the same. If that goes against your instincts, then I challenge you to consider that some more. Maybe find a place with an elevator and go for a ride and see if that statement's correct. So the scale reading, which we're calling a normal force, so I label it as N, versus the pull of gravity mg, must be one and the same in this case when it comes to their magnitudes if the net force is equal to 0. So actually our answer to number 5 is exactly the same as our answer to number 2. It would read 750 newtons. Same thing it read when the passenger was at rest. What's the reading in the bathroom scale when it descends at a constant rate? Again, 750 newtons. So whether the passenger is at rest, moving upward at a constant speed, or moving downward at a constant speed, it feels the same in every case. The contact between the feet and the floor registers as 750 newtons. It's only during periods of acceleration that the scale reads anything differently. I think this question number 7 we already answered. What's the reading in the scale when it ascends at 3 meters? Right. That's the case where the normal force was 975 newtons. So if you ascend upward with an acceleration, then you feel heavier. You don't feel that same 750 newtons of force registered by the bathroom scale between your feet and the floor. You feel a larger amount of force of 975 newtons. So that's not to say you suddenly weigh more. You don't weigh 975 newtons. You weigh 750 newtons, but you feel a contact force of 975. So bathroom scales don't necessarily always read your weight. If you were to stand on a bathroom scale in an elevator that's accelerating, it's going to read something other than your weight. In fact, what if the elevator were to descend with a downward acceleration of 3 meters per second squared? Okay, in that case, the normal force is going to be something less than the weight. See, if the weight vector is drawn longer in my free body diagram than the normal force vector, then I have a net force, if I choose to say down is the positive direction, of mg minus n. But we know net force is the same thing as mass times acceleration by Newton's second law. So we can say ma equals mg minus n. We want to figure out what is that scale reading, so we're trying to solve for n. So do a little algebra, and n is equal to mg minus ma. We can factor out the m, and the normal force would be the mass times the difference between the acceleration due to gravity and the magnitude of the acceleration of the elevator. So previously, when we calculated the 975 newtons, we had derived an equation that said n is equal to m times the quantity a plus g. Here we've got a formula that says n is equal to m times the difference between a and g. So numerically, in this case, we have 75 kilograms times 10 meters per second squared minus 3 meters per second squared, or 7. So 75 times 7 gives us what? Gives us a scale reading of 525 newtons. So you would say that it feels like you weigh less. You don't. You still weigh 750 newtons, but your contact with the floor seems less. So there's a couple things that you might have done when you've traveled in an elevator that has a large acceleration. So aren't there two cases in which this scale reading would be less than the typical 750 Newton weight? It could be when you move downward and speed up as you travel. Or it could be as you slow down on the way up. So, for example, you can get in an elevator on the 10th floor, and then you press the button to go up to the 20th floor. And at first, as you accelerate upward, at the very beginning, as you go from a state of rest into a state of motion, there has to be a larger normal force than gravity to get you to initially accelerate up. But then as you pass the 11th floor and the 12th floor, this upward force could relax a little bit so that the normal force and mg are equal in magnitude. That doesn't mean you stop moving. That means you stop accelerating. And so you would move up at a constant speed past the 11th, 12th, 13th floor, etc. And as you approach the 20th floor, the only way you could decelerate and slow down is if the normal force then becomes briefly smaller in magnitude than the weight. And so just because this free body diagram shows the downward force is larger than the upward force, it doesn't mean the elevator would be moving downward. You'd still be going from the 19th toward the 20th floor, but just slowing down as you do it. And in that moment of time, you would feel a contact force that's less than your weight. And so the trick at this point is to jump as hard as you can off of the floor, and you feel somewhat superhuman. You feel like you can jump extremely high. And it would be the exact same feeling if instead you start out on the 10th floor and press the button to go to the ground floor. Then right when you first take off, the normal force would have to be less than mg so that you could have a downward acceleration to get you to start moving. And then it could be the same conversation as you go past the 9th and then the 8th and then the 7th floor. That normal force could increase back to a value equal to your weight. And that doesn't mean you've stopped moving, it means you've stopped accelerating, and you could descend with a constant speed. And then in that case, the normal force would match your weight, and it won't feel any different in particular. Now, as you stop at the ground floor for a brief moment, the only way you could be decelerated or slowed down as you move downward is if the normal force is greater than mg. And so you would feel really heavy at this point. This would be like the example of the 975 Newton scale reading. So that would not be a good time to try to jump as high as you can. In fact, I've seen some people play tricks on each other. If there's two people in the elevator, I've seen people with their hand reach and karate chop their friend's knee right when that force suddenly becomes large and it causes the person to buckle and fall to the ground. Probably not a trick I want to encourage you to play on your friends in an elevator, but if you've ever done that in the past, now you can understand the physics behind it. So, last question. I know this has been a long video, but hopefully it's informative. What's the reading in the bathroom scale if the tension in the cable is 5,650 newtons? Okay, so there's our elevator cable, there's the bathroom scale. Let's see, let's just focus on this part of the problem here. So if this free body diagram represents the whole system, the tension is 5,650 newtons, and we found out earlier that the pull of gravity on the whole system is 5,000 newtons. So the net force has to be equal to ma according to Newton's second law, and here it looks like we have a net upward force that can be found by subtracting the difference between T and mg. Of course, we know that's just 650 newtons. So our acceleration is T minus mg over m. So this is the 650 newtons of net force divided by the 500 kilograms of the mass of the whole system. So 650 over 500 gives us an acceleration of 1.3 meters per second squared. And without a doubt, since the upward force is larger than the downward force, that's an upward acceleration. Now, it doesn't necessarily mean upward motion. It just means upward acceleration. It could be a case where the elevator is slowing down as it moves downward. Of course, this could also be a case of speeding up as the elevator moves upward. So now that we know the acceleration value, then let's make a different free body diagram. Instead of making it for the whole system, let's make the free body diagram for the person once again. So the only way the acceleration could be upward is if the contact force from the bathroom scale is greater than the weight of the person. So net force equals ma. As far as the person goes, the net force is the difference between the scale reading and the weight of the passenger. And so if we're trying to find what the scale reads, we're solving for n, and it's equal to m times the quantity a plus g. So our scale reading would be 75 kilograms multiplied by 1.3 meters per second squared plus 10 meters per second squared. Don't forget, we're just rounding up. I'm not calling it 9.8 in this problem just for the sake of making the computation a little bit easier. So the normal force would be equal to 75 kilograms times 11.3 meters per second squared. Grab a calculator, see what you get. I get 847.5 newtons. And notice that that's greater than 750 newtons. So again, this is a case where the passenger, although they wouldn't actually weigh more, they would feel heavier. They would feel like they weigh more. So there you have it. The elevator problem is an introduction to distinguishing between internal and external forces. It gives good practice in making free body diagrams, and it allows us to have an example in which we have to incorporate calculations of weight as one of the important forces in our free body diagram. Thanks for watching.